Welcome to the session organized by Discensys. Imagine all of us take out our smartphones and click a selfie. Within less than a second, the phone captures the image, improves it using AI, compresses it, stores it, and maybe uploads it to social media. Do you think one CPU alone performs all of these tasks? Yes. Today's session is about understanding why modern systems go beyond CPUs. And here, with the first slide, beyond the CPU, the architecture of specialized computing from hardware accelerators to the modern system on chip. Let's begin the session. Now, there are many examples considering large AI models, 8K video processing, real-time graphics, and network inspection falling under this as examples. So, before that, let's try to understand the title of the slide, the limits of the generalist. And modern applications demand computational power that a general purpose processor cannot efficiently handle alone, right? So the CPU handles the AI models processing billions of parameters, 8K video encoding, and real-time ray tracing, high-speed network packet inspection, and all. Making the CPU infinitely faster is no longer physically viable. The architecture itself must change. Now, uh, getting into the scenario, the real-time scenario, our smartphone story is becoming complicated, right? Suppose there's an individual named Ananya, and Ananya's phone must simultaneously run Instagram, enhance images using AI, encode the video, process network packets. Can one employee in a company do every job efficiently? Now, right? Similarly, a CPU cannot efficiently handle every modern workload. As told earlier, the workload could be AI models processing billions of parameters, it could be 8K video encoding, or high speed network packet inspection. Now, you could consider the CPU to be a school principal, right? The principal can do everything, but shouldn't personally teach every class, maintain accounts, clean classrooms, and drive buses, right? Exactly. So, what did engineers do? The paradigm shift. Now, you would consider the CPU to be general manager, which handles decision making, coordination, and operating system. Now, here, accelerator is a specialized worker, right? It handles repetitive tasks, parallel operations, and all. So instead of forcing the principal to do everything, we hire specialists. For example, maths teacher, accountant, librarian. Similarly, modern computers hire specialized processors. And here, computing evolved from one intelligent worker to an entire organization of specialists. But how do we build specialists? So before getting into it, let's try to understand what exactly is displayed here. Differentiating the general manager, that is the CPU, as well the specialist factory, that is the hardware accelerator. Right. The CPU is designed for flexibility, general computing, complex branching, and running operating systems. So as told, the analogy, the general manager who can handle any task, coordinate teams, and make complex sequential decisions. The specialist factory designed for one specific workload, massive parallelism, and fixed function operations. Now here the analogy what we assumed is the specialized factory floor built to manufacture exactly one component millions of times a second. Right. So focusing on the question, how do we build a specialist? Right? So moving ahead, through the slide here, designing hardware for the math. Now let's understand through the software approach as well hardware approach. Say in the software, suppose we repeatedly multiply huge matrices for AI. Right? CPU executes millions of instructions. Engineers physically design circuits dedicated for matrix application. Now, you could also imagine preparing tea. That is, the first way you actually read the recipe every single time if you are just a beginner. Or buy an automatic tea vending machine. And that is quite simpler than preparing tea on our own, right? So, which is faster? The machine, absolutely. So, specialized hardware is like building a machine whose structure itself performs the task. And here, the chip itself becomes the algorithm, right? So, you could also understand, so the image displayed here as per the flow chart. In the software approach, it is done using general CPU instructions from fetching till write back, including decoding and executing. But in the hardware approach, it is designing physical hardware specifically for matrix multiplication. Instead of writing software to instruct a general chip, we build a chip whose physical layout is the algorithm. Right. So focusing on the question, does this idea created act as an entire hardware ecosystem? So in order to understand that, let's get into the hardware ecosystem, right? And this idea created an entire hardware ecosystem. So moving from left to right, that is from CPU till ASIC. The CPU could be a general manager, right? Because it manages things. So here you can see the CPU general purpose, designed for flexibility, general computing, complex branching, and running operating systems. So it handles and manages all of these things. So it could be termed as a general manager here. And then the GPU could be termed as or considered as mass prediction department. Now why? So under the GPU you could see graphics and parallelism, which is originally for graphics and now heavily used for AI, scientific computing and parallel simulations. So it produces all this. Coming to FPGA, which acts like a custom workshop, the reprogrammable hardware. So it can be configured post manufacturing for specific task. And coming to NPU TPU, here the neural processing is done and it is specialized for neural networks, matrix operations and deep learning. And coming to ASIC, which you would consider as a dedicated factory, right? So here you could see it is application specific. So Bitcoin mining, fixed video codecs, designed for a single specific task, and that is why we call it as application specific. So our software or smartphone company is expanding and different departments now perform different jobs. So no processor replaces another. Each processor solves specific problems, as like CPU is for general purpose and GPU is for graphics and parallelism, FPGA is for reprogrammable hardware, and NPU or TPU, which is for neural processing, and ASIC is always meant for application specific programs. So it is somewhere like, should a doctor perform legal work? No, absolutely. So no single processor is best at everything. And here let's meet some important specialists. The intelligence and the media codes. Now introducing the three specialists, that is DSP, digital signal processes, And then coming to NPU or TPU, where NPU is termed as neural processing units, and TPUs also. Coming to ISP, that is image export, or sorry, image signal process. So going deep under DSP, you could see it is like a signal export which handles audio, communication, radar. So when you speak during a phone call, DSP actually does remove all the noise. For example, AirPods noise cancellation. Now coming to NPU and TPUs. It is an AI expert, right? It handles face recognition, speech recognition, and AI inference. Suppose when your camera recognizes your face automatically, then you could understand that NPU is actually working here. And coming to image signal processors, the ISPs, they act like an image expert, handling the brightness, the color, the white balance, and all. So when your selfie looks beautiful, even in poor lighting, then that is where you have to thank the ISP, that is the image signal processors, because it actually handles very well the brightness, the color, and the white balance. And modern systems also need infrastructure specialists. So getting into it, the title offloading the infrastructure, that is the infrastructure specialist, what we understood. Now here let's meet three more specialists: the networking accelerators, the cryptographic accelerators, and the storage accelerators. Now here the network accelerators, it manages the traffic, somewhere you could call or you could understand as a traffic police, right? So you could see it handles high speed network hardware, that is handling packet routing, load balancing, and firewall processing. And coming to cryptographic accelerators, they are actually handling security. For suppose whenever banking apps, HTTPS, VPN are used, these accelerators perform encryption. Now the reality you could understand as like a specialized lock manufacturing unit. So you could understand here as the cryptographic accelerators are specialized hardware executing AES, SHA, RSA, and ECC algorithms much faster than software, essential for HTTPS, VPNs, and secure banking. That's true, right? And then moving to storage accelerators. Now here they manage SSD operations. For example, the compression, the error correction, and all. So when your phone saves photos reliably for years, and that is made possible through the storage accelerators. You could also get deep into it, like the modern SSD controllers running dedicated hardware for error correction, wear leveling, and on the fly compression or encryption. Now, how are these specialized chips actually manufactured? Right? And that would be without raising up. So, this slide becomes a manufacturing story. That is, getting into the manufacturing design, FPGA versus ASIC. Now, as we done FPGA to be considered as flexible workshop, right? Also, the field programmable gate array, which is actually the name, right? So it can be redesigned. For example, research labs, AI prototyping, and all, right? So technically, it is reprogrammable hardware, can be physically revived after manufacturing, and it is highly flexible, used for prototyping and evolving AI inference. But what are the fallbacks? It is actually consuming a lot of power, right? And it has lower raw performance. And coming to ASIC, we have termed it as a permanent factory, and its abbreviation is application specific integrated circuit. We could recall the ASIC to be application specific always, that is built for one single purpose only. For example, the Bitcoin miners, phone AI chips, and all. Right. So, getting technically into it, it is a fixed function hardware built permanently for one specific task. The absolute fastest performance as well, and then it consumes very low power, which is available. But as every product or any unit it might be, there exist flaws always, right? So under this, the flaw is that it cannot be reprogrammed as like FPGA, right? And it doesn't focus on maximum efficiency as well, doesn't ensure zero flexibility as well. In the sense, it focus. I mean, it provides zero flexibility as well, doesn't ensure maximum efficiency. Now, you could confuse in between, like which is better for experimentation. And there comes up the answer FPGA. The reason is it is a reprogrammable hardware, which is actually an advantage over all of them. And which is better for mass production. And there comes the ASIC. Now, one specialist exists. Once specialist exists, and they must communicate efficiently. So, in that process, this slide becomes very much important and holds a lot of importance, right? Before getting into it, let's get to the title: the system plumbing the DMA bypass. Without DMA, CPU becomes middleman. Imagining every document in a company must pass through the CEO, right? And that is actually the reality. So, it's hours. CPU wastes time transferring data, but with DMA, specialists directly exchange information. For suppose, it is like employees communicating directly instead of always involving the CEO. Now, understanding without DMA and with DMA in detail. The bottleneck, that is from main memory till the accelerator while having CPU in between, right? The CPU is trapped, acting as a middleman, wasting cycles, just moving data. Now, the solution, what could be done? The CPU issues a single command, and the accelerator fetches its own data, avoids CPU bottlenecks, lowers latency, and frees the CPU to manage the operating system. So, DMA frees the CPU from unnecessary data movement. And now, modern devices integrate everything even further, right? And that is what happening here. So, coming to the integration, the modern SoC. Now, you might find out or figure out what is SoC. So here, SoC is termed as system on chip. So coming to the scenario again, previously different departments worked in separate buildings. Now, entire company works inside one building. Now what are the advantages you can understand here? The shared memory, the lower latency, the lower power consumption. Now, coming to the architecture, modern devices integrate CPUs and multiple specialized accelerators into a single chip. That is what system on chip, the modern SoC. So, the shared memory. Instead of copying data between different chips, accelerators access the exact same memory pool, eliminates data movement overhead, drastically lowering latency and saving power. So everyone accesses same information. But coming to scheduling, that is the accelerator scheduling. The operating system acts as a dispatcher. General apps route to the CPU, 3D graphics route to the GPU, voice processing routes to the DSP. So here operating system acts as a manager. Now, why work between buildings when everyone can work in the same office? Right. Now, let's see this architecture in action. The anatomy of device, the smartphone camera. Now, from the pressing the shutter button, suppose a user presses shutter and their ISP processes raw image, and then upon that NPU improves image, and then encoder converts image or video, and then cryptographic engine encrypts it, and then storage saves the file. So in order to understand this deeply, let's get into the slide displayed here. Under ISP, the image signal processor, it instantly handles raw sensor data, adjusting white balance and basic noise reduction. So as told, ISP handles the images very well. That it adjusts the white balance, also removes the unnecessary what do you call unnecessary disturbance in the image. As well, it also can handle the basic noise reduction, right? So moving to NPU, takes the ISP frame and applies AI to enhance lighting and recognize faces. Coming to the video accelerator, it encodes the sequence into H.265 file format. And coming to storage accelerator, encrypts and compresses the final file directly onto the SSD. Now, here a seamless user experience is actually a highly orchestrated relay race between specialized hardware. Did anyone think so many processors were involved in taking a photo? Right? And that is actually the magic here. That is never realized. The same philosophy exists in cloud data centers. The data center scale, SmartNICs and DPUs. Now through this scenario, imagine Amazon servers and millions of requests arrive and CPU becomes overloaded. And then the solution is with the SmartNICs and DPUs. For example, in a real-time scenario, it is like a large airport and there's a dedicated staff managing security, luggage, boarding. Instead of pilots doing everything, right? And this is how the work is managed. So, SmartNICs and DPUs offload infrastructure tasks from CPUs, right? So now getting technically into it very deeply from the problem, in massive cloud environments, CPUs waste massive amounts of power just routing network traffic and encrypting data. So yeah, that would be a solution for every problem. In the same way, here the solution is the smart NICs. The network interface cards with onboard processors, and DPUs data processing units, right? They function like how is it working in the backend, or what is it doing, right? They intercept, filter, encrypt, and route data before it ever reaches the main server CPU. The infrastructure tasks are offloaded, leaving 100% of the CPU available for actual applications. Now, specialization is very powerful, but it introduces challenges. So, coming to the friction of specialization, the programming complexity. Developers need CUDA, CUDA, OpenCL, Vulkan, and all, right? So, developers cannot write or standard code. They must use specialized frameworks like CUDA, OpenCL, Vulkan Compute, or SYCL to access the hardware. It is something like each specialist speaks different languages. Like one speaks English, one speaks French, and the other one Japanese. And there, communication becomes very difficult. The compatibility issues. The code written for one accelerator may not work efficiently on another. Right. So specialization improves performance but increases complexity also. Now, coming to the hardware compatibility, relating it to the compatibility issues, right? What we have spoken so far. Code optimized for one manufacturer's NPU rarely runs efficiently on others, right? That is, suppose a code is optimized for one NPU and that rarely runs the same efficiently, but it is not possible for that efficiency to be carried on another NPU. Now, coming to the data movement overhead. Offloading isn't always faster. In the sense, if a code is done somewhere, then moving it from that device to another device is not always easier. Right? In the same way, the same scenario, offloading isn't always faster. Moving data to an accelerator takes time. If the task is too small, the transfer latency negates the computing benefit. And coming to the cost and lifespan, which is actually very much important because computing absolutely depends on the cost we are bearing and lifetime it actually works, right? So the cost and lifespan. Highly specialized hardware like early AI ASICs can become obsolete or obsolete rapidly as algorithms evolve, right? So where is this evolution heading next? The future of specialization. In the current state, deep integration of dedicated AI and security processes directly into all consumer hardware. Right? You could see from the image having photonic accelerators and quantum accelerators. Under the photonic accelerators, they use light instead of electricity. So, what are the benefits that could be achieved? They are the higher speed and the lower heat. It is somewhere like replacing roads with high speed bullet trains so that work is done very faster. Now, coming to quantum accelerators, it solves impossible problems. For example, the optimization and the cryptography and many more. So, quantum processes won't replace CPUs directly. They will act as extremely specialized co-processors. Right? You could see here the co-process designed to solve optimization and cryptographic problems that are mathematically impossible for classical binary chips. So moving ahead, the ultimate mental models. Having a recap of what all is explained so far, right? So in the hardware and the mental model, the first comes the CPU. It is actually acting like a general manager, right? And the GPU acts like a factory workforce, right? The massive parallel processing engine for graphics and broad area workloads. And then the NPU, which acts like an AI specialist, right? It is built on a purpose for AI inference and matrix math. Coming to DSP, it acts like a communication expert, right? Because it is optimized for real-time audio and communication streams. And coming to the FPGA, it acts like a Lego workshop, right? The blank canvas of reprogrammable hardware. And then the ASIC, acting like a permanent factory. The fixed function hardware optimized for absolute maximum efficiency. So, modern computing is no longer the story of one powerful CPU. It is a story of many specialized processes working together as a highly coordinated system or highly coordinated team. So, modern computing is heterogeneous. Every component now performs exactly the work it is best suited for or it is specialized for.